season of UK talks. Today we have two amazing speakers. The first one is Maria Battarra. Can you please share your screen while I present you?
Yes, it's coming.
Okay, great.
Here we go. Shall I start, Margarita? Yeah.
Yeah, just quick introduction. Well, thank you again, Maria Battarra, for accepting our invitation to this optimization talks. Maria is a professor in operations research at the University of Bath School of Management. So please go ahead.
Thank you so much, Margarita, and thank you so much for this very kind invitation. It's a pleasure to be here and present my research. This work started very much thanks to Gonja and Mustafa, that are our collaborators and co-authors from Turkey. They both live in Izmir, a lovely town in Turkey, and they inspired this work with Güneş as well. I picked this topic because I really like to give this talk. First and foremost, we know our wildfires are important and very, very dramatic these days. They are always in the news in the summer. But I also found this area of research very interesting from a modeling perspective. And I think there is a lot that we can contribute as a community. So I hope you will find it inspiring and some good ideas might come to you as well. So what is the motivation? I think you know way better than me what's going on in the news. The wildfires are a bit everywhere. We still have the memory of the LA terrible images, but all over the world. Turkey is a very wildfire-prone country, Italy is, Spain is, and we can name many. And when we speak of wildfires, we can think not only about the terrible effect on human lives and the environment and the forests, but also we can quantify the effect of wildfires, even purely from an economical perspective. They are a disaster. I was checking some numbers before, and in terms of insurance costs that have been claimed, it's estimated that LA wildfires will account for $30 billion. And the figures here that you have on the slide in US in 2016, so probably even not an updated figure, is quite scary. And when I looked at the data for UK, that is the most wet country in the world, it rains all the time, so you wouldn't expect wildfires. Actually, there are quite a few, and even from an operational perspective, even speaking with the operational research expert in South Wales, it is a very tiny country and a sub-part of the country. There have been in 20 years 75,000 calls for emergency situation and a wildfire. So it's spread not just anymore in very dry and hot countries, but it's actually an emergency that is widening globally. This is data, for example, from the UK, and is estimated that depending on, the two plots are varying depending on the increased temperature, but it's estimated that by the end of the century, the risk of a wildfire will increase up to 1.5 times. And we are speaking of wildfires that can cause casualties and major disasters. And when we speak of wildfires, we don't need to think only of the immediate effects, but wildfires also are one of the main contributors to climate change. So if we are looking, for example, at CO2 emission, 5% of the CO2 emission is more or less estimated to be due to wildfires, because obviously the heat and the burnt gas is contributing quite exceptionally to this phenomenon. So when we are speaking of net zero, then we can also think of wildfires as one of the main contributors. And if you think of, for example, the amount of CO2 emitted in 2022 by wildfires, that was basically the second largest contributor among all the countries in the world, rather than China. So wildfires are actually a very important aspect. So when we are dealing with wildfires, we are obviously saving lives, we are saving nature, but we are actually doing a lot for the planet. There are many possible contributions. It was very interesting for us to start looking at the literature, because actually there is a very wide literature in this area. Even in forestry journals, you will find very good mathematical models and operational research techniques that have been applied to wildfires. I'll just screenshot a couple of examples for you in case you are curious and you want to start looking into this domain of research. But our goal was started very practically, because our colleagues, Gonja and Mustafa, had a contact with the Forestry Directorate in the local area where they live, in Mula area. And they asked for our help, because when there is a massive wildfire, they need to coordinate a lot of resources. Because when there is a wildfire, obviously they dispatch firefighting teams. They dispatch fire helicopters, but another contributor is fire break constructions teams, I call them here. It's basically teams that raise the forest. They take it down to the ground so that the fire cannot spread. In their case, they just have contracts with the local mines so that they can rent some bulldozers in case there is an emergency. So they want to make sure that their plan of action to respond to wildfire is as effective as possible given the resources available, and the damage to the forest is minimized. I'm not going to go through an extensive literature review, but if I have to pinpoint you to three main problems that have been already studied in the literature, the wildfire containment problem, this is one in 2003 has been proposed, looks at how to create a perimeter around the fire area, around the wildfire, so that the fire gets blocked as soon as possible. And in this case, there is a resource, generic resource, that is used to create a perimeter around the area. And the perimeter usually is considered as a line. So there is not a detailed map of action. This is done in the firefighter problem, where in this case, this model is mostly thought for firefighters. So they consider a rasterized grid of the forest, and they decide on the position of the different firefighters over time. And then there is another approach in which the idea is that one of creating barriers. So lines that protect the fire from extending in different directions. So again, some of these approaches are more geometrical, and they are thought more, for example, for razing teams, and others are thought more for firefighters. And other again, they think of this line of protection as mostly a geometrical resource without specifying their operational needs. In our case, we were looking exactly for an operational plan. So the main contribution of this paper, that is published in Nature, if you are curious to look for more details, is that one of really find what to do with each specific resource so that we consider their operational needs, their operational strength, and we can find a synergic use of all the resources. So we started with the modeling the environment, a forest. And we're considering the forest as a grid of cells that are flammable or non-flammable. For example, if there are rocks or if there are rivers or lakes. We're considering roads, because obviously in the forest we can still have roads where, for example, our fire engines can pass. And we have different priorities of flammable areas. So some areas are residential areas, so we want to protect houses more than we want maybe to protect purely woodland. And we can create a relative importance between areas that can or shouldn't burn in the case of a wildfire. And we also looked at the literature on how fires usually spread. And typically, the pattern of a spread of wildfire is that one of an ellipsoid that follows the direction of the wind. So if the wind spread in a certain direction, the fire will tend to spread in that direction faster, a bit slower on the side, so the flank fire. and even slower toward the back of the direction of the fire. So if you want to get an example of how we are modeling the forest and the spread of a fire, you can see an example of forest in which there are roads, the white cells, and rockery or lakes, so non-flammable cells, the blue ones. Time 0, we have a fire in this red cell. And then after 1 hour, we are assuming that that cell is completely burnt, so it's black. But now the fire is spread 1 backward if the direction of the fire is towards south, the wind is towards south. It has spread 2 maximum on the flanks, so on the sides, and up to 3 toward the direction of the wind, so south. And you can see as over time, if you don't control a fire, more and more cells will be burnt, and the cells that are actively on fire keep on spreading in the map. So our goal now is to find the best possible way of using our resources to block the spread of the fire on our grid. So we want to minimize the damage on the forest. And the damage here is not just the fire that is burning the forest, but could also be the destroying action of our resources, because when we are razing the forest, we are also destroying it. Maybe we are not having fumes and bad emissions as much as when we are burning, so there might be a different weight, but that's still something negative for the environment. But our contribution is that one of modeling the details and the requirements of each resource. So for example, we want to model the fact that not all the resources will be available at time 0. Some resources might arrive later, some will have breakages or periods of shifts, or they might take longer to operate on a certain cell. Bulldozers need to be very far away from the fire, because otherwise it's dangerous, because the fire progresses quite fast, whereas fire engines are faster to move. Some resources are slower or faster, as I mentioned, or some resources can only move on the forest roads, like the fire engines. So we need to make sure that those are only accessing the fire through one of the roads. So we model this problem, and it's a lot of binary variables. So if you like binary variables, this is your kind of modeling. We first have a set of variables that describe the forest situation at every time instant. So we will have variables depicting if there is an active fire on a cell, variable Z, if a fire is currently intersected, so treated by either a fire engine or a fire helicopter, and that's variable S. We have variables U that say if a cell is already burnt. And then if a variable V says if a cell is razed, so it has been taken down to the ground by one of our bulldozers. So with these 4 states, we know exactly each cell situation in every time instant. And then we need to decide on the action or operations of our resources. So we will have variable X saying which cells, if a cell is razed or not at time t. We have variables U that decide if an helicopter is currently operating on cell I at time t. And then for the fire engines, we need 2 sets of variables, because P variables tell us which cell is currently extinguished by that fire engine. But we also need to decide on the parking spot. We need to make sure that the cell I is extinguished while the fire engine is parked in cell J. And the cell J has to be on one of the forest roads. So in this way, we make sure that all the operations respect the needs of the different resources. I'm not going to go into the details of the formulation. You can find it in the paper. But as you can see, in our objective function, we are minimizing the damage due to uncontrolled fire. due to the cells that have been, where the fire has been intercepted by a fire engine or a fire helicopter, and the cells that have been raised down to the ground. And as I said, there is a different coefficient here to take into account the different level of damage. This constraint is to initialize the fire starting point at time 0. Then we have different variables that say what can happen in a cell at any time instant. These constraints here, as you can see, link what's happening at time t-1 and what could happen at the next time instant in terms of progression of the fire and progression of the state of the variables. And then, as you can see, these variables link if a cell is going to be burnt at time t, if a cell is raised at time t, depending on the operations of our teams of razing. We have variables S that say if the fire in that cell has been intercepted by one of the fire engines or fire helicopters. We have additional constraints here to say that a resource might not be available at a certain time slot, because some resources need to travel from far away, so they will arrive on site later. This set of constraints here are defined based on the number of resources we have available and how many time units each resource will take to complete the operations on one cell. So these constraints are allowing us to define the amount of resources available. And then we have these constraints here, xijt. In this case, we are saying that when we are razing, we can only access that cell if a nearby cell has been raised, because also the bulldozers cannot pass on top of a forest that is still available. And in these last two constraints, we have safety distances, because obviously the bulldozers need to be farther away than fire engines. There is a lot of smart preprocessing in this formulation, because if we know in advance information about the wind, we can define a subset of cells for which the fire will spread, and a subset of cells at any time instance in which the operations can take place. We were very pessimistic about this formulation because obviously so many variables on a large grid. We thought, okay, we will never be able to solve any problem. And actually this was not as true as we thought. But in order to speed up computation, we used some tricks. Obviously, one trick is to bound the grid of the affected forest, try to keep it as small as possible. And we also limit our analysis to 10 hours, 10 time steps. If the fire explodes and it becomes like a 2 weeks problem, I think this model is not suitable. You probably need to decompose, you might need heuristics, or you might need a more macro approach. The other idea that we had was that one of variable reduction. We thought we let the fire go as if there were no resources. And that one gives us the fastest time at which the fire can reach any cell. Because obviously, as soon as we put boundaries, the fire will go slower. With that information, we can then block a lot of variables to be 0, because there will never be a burnt cell, there will not be active fire, and there will be not any action of extinguishing the fire on that cell. So by modeling the simulation of wildfire without any restriction, we can already decrease the number of variables quite substantially. But the only methodological trick that we used was a Bender's decomposition rather than the basic ones that I explained. We realized that there is a symmetry between the operations of the fire engines and the fire helicopters. So if we know which cells are currently treated by fire engines and fire helicopters, there are many possible solutions in which a different position of the fire engines and distribution of which fire helicopter takes care of which cell are feasible. So we thought about projecting the Y, W, and P variables that are basically where our resources, fire engine, fire helicopters, are currently operating, and solve a sub-problem. I'll show you the sub-problem in a second here. That basically says, given the amount of helicopters and fire engines we have available, and the fact that each of them can only operate on one cell at a time, is there a solution that allows us to extinguish all the cells that the master problem has suggested? If it's feasible, we have found the optimal solution, because we have found that resources can tackle the cells that the master problem has suggested as to be extinguished. If not, we can include a combinatorial Bender's cuts that says, no, these cells cannot be treated, cannot be intercepted by a fire engine or a fire helicopter. So this solution is not feasible. Okay. So let's see some results. First, we started with smaller instances. We were not optimistic. So 25 by 25 grid, 50 by 50, and 100 by 100, small, medium, large. And different number of ignition points, different number of resources available. We used Gurobi for 1 hour. And most of these parameters come from the real example I'll show you later. The first result is that the Bender's decomposition works very well. So if you can see, this is the standard formulation. This is the Bender's decomposition. We managed to solve all but one of the instances, and the gap is only 0.1. So the Bender's decomposition works very well, and it's nice to see once a Bender's decomposition that has a practical visual interpretation, the symmetry between the work of fire engines and fire helicopters and their position on the map. But then we came up with more insights. For example, how important is to have a weather forecast? If we know that in time, after 5 hours, there is a wind change direction, and the fires start turning toward east. So if we have a reliable weather forecast, what's going to happen? Well, we are in one set of instances. This is the number of resources and how many instances there are with those resources. In one case, we get the same solution quality. But in all the other cases, we can improve up to 11%. So a good weather forecast about the wind allows us to prepare the barriers for razing teams in the right direction. Because in that direction, at the moment, it's not dangerous to prepare a barrier. We can stay at a quite small safety distance. And then when the wind will change, the barrier is already in place. So that was interesting to see and visualize. We also saw which are the resources that are more important to have on site as soon as possible. And those are the fire engines. But I'm running out of time, so I'll go very fast. And we also checked what's happening if we have more roads. So a situation in which we have this amount of roads in our forest and an extra road in our forest. And as you can see, if we run the model per se, we get a 5.4% reduction in the damage to the forest. But when we take into account the damage due to destroying some cells because we are building a road, in our instances, it went on average to 2.9. This is not always the case. In one of the instances, actually, we are ruining the environment, but we are not decreasing as much the damage if there is a wildfire. So adding extra roads might or might not be beneficial depending on the specific instance. It's something that should be tested. And to finish, I'll show you what we did then with the realistic instance. So we did map the area of Mula. Goja and Mustafa did an amazing job in checking where are the streets, where was the most precious type of forest, the least precious type of forest, the rockery. And then we run our model. And as you can see, if we simulate, for example, a fire in this position, that one is how it expands in 1 hour. And now we can see how our teams are gonna be operating. The orange is the fire helicopter. Those are very expensive, there are very few. And the razing teams are coming to start preparing some barriers. The yellow ones are the fire engines that are starting to protect this side of the forest. You see the fire engines are very close to the fire front, whereas the razing teams are far away. ×3, the fire engines are moving toward the bottom. They're blocking the expansion of the fire here on the south side. And the fire is starting to expand toward east. So the barriers now start moving in this direction, considering the future expansion of the fire. So fire engines, again, working very closely at the boundary of the fire, and a barrier that is starting to be created at the south. And as you can see, the forest now gray is raised, so it's still damaged, but that barrier is going to block this expansion down south. And after 8 time instance, in this instance, we managed to fully control the fire. Even if the damage is the black ones, cells that are burnt, and the gray ones, the cells that have been raised. I know I went very fast. I hope I gave you a good idea of what we did and the nature of the application. I think it was very interesting for us to see what we could solve. We were not as optimistic because the instance we solve is actually 183 by 164 cells. So quite a realistic instance, and there are a lot of binary variables in it. We think that the decomposition technique was very effective, and it can lead to test a lot of possible scenarios in real life. But a lot of extra work is needed for longer horizons, for routing the different resources, for extra fires that can spread over time. So there is way more to explore, and I hope many of you will be inspired by this talk and will start working on this research area.
Thank you very much.
Thank you, Maria, for your talk. So I just want to remind everybody that we will have break rooms at the end, so you can ask Maria and Carmel any questions after their talks. So now we'll leave Sylvia to introduce our second speaker.
Yeah. Carmel, can you start sharing the slides?